To find the roots of polynomials, MATLAB has many built-in functions which implement the numerical methods that we saw so far. And one of these is F0, which is very popular, and it enables finding the roots of single functions. And there is also roots which find polynomial roots. Poly construct polynomial with specified roots. Polyval and polyval m evaluate polynomials and polynomials with matrix argument. The residue partial fraction expansion, the residues. The polyder differentiate a polynomial. Con and the con, these are the multiply polynomials and divide polynomial functions. So you can see these and use them to be able to find the polynomial. Especially F0 is very functional, and we will show how to implement it in the following slides. In this slide, you can see an example for using MATLAB to be able to find the roots of a polynomial, and we will use F0 function to find the roots of this x to the power 10 minus 1 polynomial. And we want to have the interval to be between lower bound 0, upper bound 4. And because F0 actually accepts these, so two initial guesses which will have lower and upper bounds. And we know that the two roots will occur at minus 1 and 1 because this is x to the power 10. It's an even number, so there will be multiple roots. And if you remember, in example 5.6, we used the false position and bisection methods in chapter 5 with initial guesses of 0 and 1.3 to determine the positive root. And now we will use F0 function. And the F0 function is designed to locate one root of a single function in MATLAB. So a simplified representation of its syntax is like this. When you write this to MATLAB, you can easily get a solution. So this f is the function you are analyzing. X0 is the initial guess. The options are the optimization parameters, and these are changed using the function optimset. We will use this. We will show that in the following slides as well. If the options are omitted, in other words, if you don't use this, you can just use these, and then the default values will be used. And also, in this F0, you can either use one guess or two guesses. So here in the example, we will have two guesses, but you can also use one guess as well. And if two guesses are employed, they are assumed to bracket a root. So if you want to use two guesses, you have to use a bracketed guesses actually. It will assume that the lower bound and upper bound are given, and they should be bracketing a root. Or even if it doesn't bracketing the root, it assumes that way, the F0 function. So based on this information, let's use F0 to solve this function in the following slide. Here you can see the solution in MATLAB to solve the equation and find the roots of the function using F0. So basically we defined the initial guesses as 0 and 1.3. Let's start with that, and because in example 5.6 we use those. If we use them, so the F0 function in MATLAB will be used like this, and at x means x is the variable, and this is the function. So this is the first term of the F0 function, and this is the second term. The second term will involve the x0, which includes the lower and upper bounds, as you can see here in a bracket. Bracket means actually there is two values in a row of a vector, so you can define a vector here. So this can be either one guess or two guesses. It can be only two, for example, maximum two. When you type enter, it will give you the result of x equals 1. So it will easily find the solution. If 0 actually the numerical methods worked at the background and gave you the results equals 1. In a similar fashion, we can use initial guesses of minus 1.3 and 0 to determine the negative root, because we said that initially we assume that we know there are two roots, 1 and minus 1. For 1, we actually bracketed it between 0 and 1.3. And for minus 1, we bracketed it between minus 1.3 and 0. And you just simply change this and use the same F0 function, and when you enter, you will get this minus 1 result. So these are the bracketed values. You can also try different values if you want to see if these will converge or not. We can also use a single guess, as we said, if 0 accepts it. And for example, if we say the 0 will be the initial guess, then we can use the same thing, and this will just be a variable instead of having a vector like this. So then, in this case, we will get x equals -1. As you can see, for this case, the underlying algorithm happens to home it in on the negative root. It doesn't find 1, but finds -1. To find 1, maybe you should change this to 0.5, 0.8, or 2. Then it can give the positive value as well. You can have you can give it a try different initial guesses, either bracketed or not bracketed, and see the results and understand how the results are changing. We can also use the optim set term as an additional input for the f0 function, and this optim set actually defines the options for the f0 function. And we said, for example, disp and iter. That means this shows the results, as you can see here, the function iterations actually, and the results here. Actually, it shows the iterations because with display we defined to show the iterations. So it will show each iteration, the x values changing in it, and the fx values, and the procedure. So basically search, interpolation, bisection, interpolation. These are just the numerical methods that it is using. And we used this for only one initial guess, 0. We mentioned it earlier, and if you remember, it found -1. It gave only this result to us before because we didn't use this option here. But now we are using option. That's why it is showing all the details of iterations. So you can see that there were like 35 iterations at the background. And it started with a search approach, basically. And after that, there was an interpolation approach, probably quadratic interpolation, or it can be linear as well. We should check the maybe help file of the f0 to see what this means or this means. Then here you can see that it changed to bisection method, then again to interpolation. So basically this is similar to Brandt's method, and it is using different methods in a hybrid way and in a combined way, starting from search method because it's an open method. It's just using only one guess initially, so it started with 0, and you can see that it reduced to minus, then positive, then minus, negative, positive, negative, positive, and actually it is not converging, but maybe having a sign change. And we can see here the function has a sign change actually. Then it says looking for a 0 in the interval of -128 and 0.9 over here. Then it turned itself to a bisection over here, then converged to a result -1 around -1, then moved on to interpolation again to reach to exact value, and it found a 0 in the interval of this, and it gives this eventually. You can give it a try in MATLAB and see if you can get the same results. You should be able to get the same things when you use option, or not using option. You can see the results, they will be the same. In this slide we have another example, example 7.7, and we will use MATLAB for polynomial roots. Here we have actually a fifth degree of polynomial, you can see, with different terms. It's more a longer, let's say longer polynomial compared to the previous example. And in this we will have actually also complex roots, and we will see if the MATLAB can find the complex roots as well, because in the previous example there were only real roots. Here there are the real roots but also complex roots. So the polynomials are entered into MATLAB by storing the coefficients as a vector. So we will store these coefficients as a vector like this, all of 1, 3.5, 275, 2, 125, 3, 785, and 125 here with the signs as well. And when we use polyval with a, and if we say x equals 1, actually this is the initial guess, or sorry, not the initial guess. This is, we are just evaluating this function using these, and because it has 1, 2, 3, 4, 5, 6 terms, it understands that this polyval, this is with 6 terms, term minus 1 degree, so 5th degree. 6 terms means 5th degree. So it solves a 5th order polynomial with these values or the coefficients for x equals 1, and it just plugs in 1 here and so gets the solution. We can also get the derivative by using polyder, and you can also again use the same coefficients, so it will get the answer for the derivative as well. Simply you can see that this derivative is this, and when you say polyder A, the derivative of this gives the same coefficients of this, so it can calculate the same. Let's continue to the solution in the next slide. In this slide we will continue to example 7.7, but we will show the division. If you remember, we were using division and it was creating some round of error due to deflation, and we will see that here. For division, what we want to do here is that we want to create a quadratic polynomial that has roots corresponding to 2 of the original roots of this function. Let's say the roots are these, and for these the quadratic is x minus 0.5 and x plus 1. So if we multiply these, we will get this quadratic function, and this has these roots, and we can define this in the MATLAB by defining the coefficients as a vector over here. And this vector is a function now, and in the previous slide we showed that a vector was this function. So with this decon, we want to divide the a function, which is this one, by the b function, which is this one. So when we divide them, it will give us 2 values over here, and these 2 values shows a 3rd order polynomial d, because we divided a 5th order to a 2nd order, so it should give a 3rd order polynomial, and a remainder e. Remainder means maybe these are not divisible and there can be some remainders, but here it seems it is divisible because actually these are just multiplications of these. That's why these are 0. If these were not multiplication of these, it wasn't able to be divided like accurately, so there would be some divisions here, but it is not the case for this function. So because the polynomial is a perfect divisor, the remainder polynomial has 0 coefficients. This means the 3rd order polynomial is directly written using these coefficients like this. So this was the result of the division of the 5th order function. And now let's continue to the solution of example 7.7. Now we divided the function to a 2nd order polynomial, and we obtained a 3rd order polynomial for which the coefficients were defined with d vector. Now if we use roots, it will calculate the roots of the d function, and the expected result is that the remaining roots of the original polynomial are found as these, because 0.5 and the other value actually were found already. This 0.5 and minus 1, we divided by them, that's why the remaining ones were these, and we found them. So we can now multiply d by b to obtain the original polynomial, 5th order polynomial, and we can have this multiplication using con function d and b, and it will give us the coefficients of the 5th order polynomial. You can see the same coefficients we obtained as expected. Finally, we can also use roots to determine the roots of the original polynomial. When we say roots a, because a had all of these, we simply get all the root functions, as you can see here. We have 5 roots, 3 of them are real, 2 of them are complex. And with this example, you saw how to use roots to get the root of this polynomial. Also, multiplication, division of the function, calculation, a value of a function, and a derivative of a function. You saw these functions, how to use them for an example. And you can use the same ideas for different polynomials and get the roots, or divide them, multiply them, or get the derivative of them. And this is the end of chapter 7, in which we learned about the polynomials roots, or roots of polynomials. And we saw that MATLAB can be used with f0 function as well as some other functions like roots to get the roots of polynomials. And please read section 7 in the book to get more information about these. You can also read section 8 in your book because it has some case studies for roots of equations. Some engineering applications on how the root finding is achieved by numerical methods. We will not see these in this course, but you are free to read and have some more ideas about those because you may need them in the future. And thanks for listening. See you in the other classes.